Yes, fine.
Okay, great. So, uh, um, two lecture before, we just did counting distinct elements, but it was using an idealized hash function. Today, we will see a different algorithm for counting distinct elements in a stream, but using the hash functions that we saw last week. Okay. So what is our question? So we want to estimate distinct elements. So you're given a stream row, and we know that these numbers are coming from 1 to n, and we would like to know how many distinct elements did we see. And of course, there's an offline solution via dictionary data structure, which we saw last time. And what we would like to do is that then we saw a hashing-based idea where we assumed idealized hash function. What do you mean by idealized hash function is that this was a hash function which was taking values in the range 1 to n and was mapping a real number between 0 and 1, and that is also fully random over the real interval. And so I'm just trying to brush up what we did last time, and we will see how we will make this algorithm today without using the assumption of this hash function, which takes a number from 1 to n and maps to a real number between 0 and 1. Okay? Okay. So, and so what we saw that suppose there are k distinct elements in the stream, then we ask what is the expected value of the minimum of hash values. So we notice that if you have 0, 1 interval, then if you have k distinct values, then basically it divides the interval into roughly equal parts. So if you have a smaller value, its value will be 1 over k plus 1. So if you take the inverse of this and return -1, and that should give you the total number of distinct elements, right? So this is what we proved last time, that if you have k random variables. So why k random variables? Because this is a hash function. So for every number which are distinct, they're just going to map to the same number between 0 and 1. So basically, if you have k distinct number, then they're just going to fall some k distinct numbers uniformly at random over the real line 0, 1. And then we were able to show that the expectation of the minimum is 1 over k plus 1. And that is why we were able to make this idealized hash function based distinct elements algorithm, which basically stored the minimum of the hash value and returned 1 by y minus 1, because as I said to you before, that it basically partitions the interval 0, 1 into k plus 1 parts. So 1 over k plus 1 is k plus 1 minus 1 is k. So we are returning this, okay? And then we did some variance calculation, and we showed again that if we do a parallel independent estimates to reduce the variance, and then we apply Chebyshev to show that average estimator is 1 plus epsilon approximation with constant probability, and then we applied median trick with log 1 over delta parallel copies to get 1 plus epsilon approximation with probability 1 over delta. So the total space was roughly 1 over epsilon squared log 1 over delta hash values. But unfortunately, the problem was that we assumed this, that my hash function is like takes values in real, and today we will like to remove that assumption, okay, by limited independence. So today what we would like to do is that do not have an idealized hash function, and we would like to use some hash function from n to capital N for appropriate choice of n, and use pairwise independent hash family H, so that the random H in H can be stored in small space and computation can be done in small memory and fast. Okay, so that's the whole goal of the today's lecture. So just going back to what we saw last time. So just to, I mean, if you did not remember the constructions and everything is perfectly fine, but just to remind you, a family H of functions mapping A to B is called T-wise independent if for any choice of range element, right? And for all distinct choices of I1 to IT in A, probability that if you choose H uniformly at random from the family of hash functions, then it takes h of I1 is A1 and dot 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 h of ik jt is nothing but product of HIL JL. And moreover, we saw that if these functions are uniform in its range, that is, it takes any value from 1 to b with probability 1 over b, then basically if you choose this function, then if it is t-wise independent, then the probability of this is 1 over b power t. And there is a known construction that for every nmt in natural number, there is a family of t-wise independent hash functions from, basically think of this as like a field of size 2 power n to field of size 2 power m, such that choosing a random function from H takes T max of nm random bits, okay? And evaluating a function from H takes time polynomial in nmk, right? So the typical application when you will apply this, n will be like polylog m, m will be like polylog n, okay? So that is why everything here will be like poly function. So just remember that given any n, m, and t, okay, we can construct a t-wise independent hash functions with a with h from f to the power 2 power n to f to power m, okay? And as we saw last time, that for several applications, it doesn't matter what the range is, because we can always have many random variables and take as many as you wish and discard others, okay? But however, how the range is being taken care of, it does matter, but we will ignore some of these things. So for all practical purposes, and let me be say completely wrong, okay? This is not how things are constructed like. So given nmt, we'll do construction using polynomials. So f will be a field and we will be choosing, and what is my function of hash family is basically selects t values a0 to a1 and n to m, and it evaluates like a0 to at minus 1. So how many such functions are there? If you notice, well, it depends on what the size of f is, and say, so this size of this family will be f to the power t, and each ha0 at minus 1 given a value I, it basically evaluates this polynomial, okay? And to notice that if you want to sample some function from here, then all you need to do is pick t random with replacement numbers from f, a0 to at minus 1, and that automatically determines ha0, a1 to at minus 1, okay? So all I wanted to tell you that if you wish to get a family of hash function which is t-wise independent from wherever to wherever, doesn't matter for now. Of course, like, I mean, based on what the range is, you have to maybe do some mod m or some other operation. But let's not worry about those things. It will just mean that you have to pick some order t numbers uniformly at random from some f, let's say p power q, where p is a prime, okay? Okay, something from these kind of fields, okay? There are lots of details here, but and this we can do it like, given, like it's like choosing number from 1 to p power q, some t numbers, okay? And given this number, we can define this function h and we can evaluate it, okay? So for all practical purposes, whenever I will say t-wise hash functions, it will mean that we are storing some order t numbers with some log, depending on what the field size is, log of that field size, okay? Okay, okay. So any question till now? So this is like extremely simplified version. If you do not remember anything, you should always just think for now, or for the purposes of this course, that we are just going to choose some t numbers from some field, and that will give us the desired, what do you call, independent hash families, okay? Okay. Any questions before we move to the algorithm?
Sakit, what is wrong about this?
Look, because I cannot construct these objects for every m, right? Right? This range m. Like just this construction alone is not good enough. You have to take some modular arithmetic and do those things so that the range. So basically what I mean that first you will choose something n and you choose something which is a prime. So you gave me a m, right? I will choose some bigger prime p greater than m, right? And I will generate there, but that is not what you wanted. So now I have to do some mod m to get to the range from here, right? So basically this will be like mod p, then another mod m.
Okay, yeah.
So I do not want to do all those things. So for for the purposes, I mean, since we already did all these things, I mean, whenever we'll say we'll choose t by independent hash families, it's like choosing some order t values, like some t plus 2 values, and based on that we can evaluate everything. Okay, so this is all that I meant. Okay, so let me first. I decided to do some other algorithm first, but let me tell you, the first algorithm to do this was in 2000. Actually, there is a previous algorithm by Alon, Matthias, and Zegedi, but first we will do this algorithm from 2002 by Bar Yusuf, Jairam, Kumar, Sib Kumar, and Trevisan. Okay. Okay. So first, let me tell you the algorithm, just the description of the algorithm, and then we will discuss why it is the way it is. Okay. So H is 2-wise independent hash family from n to n, where capital N, n cube, and we choose H at random from H. Okay. So now notice, to choose this H from this, since it is 2, you will just need some ordered log in bits. Okay. Okay. And we have initiated T C over epsilon square, C to be decided. Okay. You will see from where does C comes. And what are we doing? So if you recall, in our algorithm, for the previous hash values, we were just keeping from the hash values, minimum hash value. But now we will keep T hash values seen so far, like smallest T hash value seen so far. And rather than returning the smallest hash value, we will return the Th smallest hash value. Okay. So these are two basic differences. Okay. Now, the first question, how can you update smallest T hash value? That is very easy. Once I have seen T, so you maintain any data structure or priority queue, whatever it is, your new value has come. Either it is like, so for example, you could have kept heap. Okay. Okay. And you just check with the smallest guy, the new current item. If it is smaller than this, then it will bump out someone, or else we will ignore it and we'll keep it. So it is not very hard to see that we can keep in order T log n bits, okay, the T smallest hash values, okay. And okay, so what will be memory? Memory will be like, so we are going to store roughly order 1 epsilon square value. So it will be like order log n epsilon square bits, and also order log n bits to store hash function, right? And what is the processing time per element? Like order log 1 over epsilon comparison of log n bits number by using binary search tree or something and computing hash values, right? So all this we can do nicely, okay? But let's try to understand first thing, why Tth hash value, okay? So first of all, what is this algorithm doing? Okay, so this algorithm, so I will come to the basic understanding of this algorithm. So basically what this algorithm is actually trying to do, it is trying to mimic the same 0, 1. So this is what it is trying to mimic, this algorithm, okay? But now, rather than having a 0, 1, it is trying to say that, look, let's make NQ parts, okay? And let's be uniform over there, okay? So basically, I have divided my 0, 1 interval in some sense into a multiple of 1 over n. So 2 over n, blah, 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 and so on and so forth. So this is one way to think of this. But before I go to this, let me tell you why teeth has value, okay? Why not minimum? Okay, so the question is, we could have done this also as a minimum. So we could have also kept the minimum. But if you remember, whenever we kept minimum, okay, minimum, while storage was very nice, right? Because you were just keeping one item, right? But variance was very high. Okay, so this is something which I would like you to take away from this. But variance was very high. Then we did this averaging trick, right? We did averaging trick by computing several values, okay, and then taking the average of this. So taking some of them and then taking average, right? And this is the way we reduced variance. Okay. Now notice what happens with minimum. Like minimum is like, it's like just one value, right? And like, so suppose you had d distinct numbers, right? D distinct numbers, and you are mapping them to some interval, okay? Or somewhere, you're mapping them here. Now, chances that one guy can go off, like, is much higher, and hence it can, like, you can, what do you call? It can just mess up your things completely. But when you take median, what happens with median? So what we have noticed up until now, that if we had a median, okay, when we were storing the median of some things, then for median to go wrong, not one random variable has to go wrong, but several random variables has to go wrong, right? So in some sense, median is much more robust to outliers compared to one random variable, right? Because chances that many random variables will go far away from its expectation is much lower compared to just one value, okay? But unfortunately, if I had a d items, and I would like to store median, then this is a problem with storage, because then we could have some n log n bits, right? So rather than doing this, we say, okay, fine. Notice that, okay, we said, look, we cannot do this, but let's try to store several minimum values, and let's just return the one which is like certain higher threshold, okay? And then the chances is that this guy, so this is basically a threshold between whether to keep one random variable versus keeping several number of random variables and giving you one. So for example, by returning the teeth hash values, now I'm depending on not one hash random variable, but several random variables, like t of them, right? So for teeth hash minimum hash values to go wrong, several of them have to go wrong. So this is a trade-off between storing one versus several. And in terms of space, it's not that it is giving us anything more, because if you notice, we are anyway storing c over epsilon square numbers, right? So if you would have done averaging also, we were generally doing order 1 over epsilon square to reduce the variance, right? So either you do this averaging trick or this. So basically averaging trick is incorporated into this. And in many applications it has seen, because medians, with respect to medians, one can apply better probabilistic inequalities. You tend to get better uh, estimates. Okay, but most places wherever you can use this trick, you could have also used just return the minimum, then taken the average and reduce the variance. Okay, so I hope this is at least this idea is clear, that why we are returning teeth as values, or why people, I mean, we just hope that if we keep return kth minimum has values, right, I mean, we are doing better. Right? We have reduced the variance. So this is just a hunch and it seems to work. Okay. So I hope I have made you understand why teeth has value. Okay. Any question? Okay. So now let's go back to some intuition for algorithm or analysis. Okay. So let D be actual number of distinct values in a given stream. And we will assume that D is more than C over epsilon, because if D is less than C over epsilon square, we can keep track of them exactly by just keeping one some data structure. And if it is more than that, you just ignore the data structure, right? Because whenever a new element comes, you just check whether that is there in the data structure or not. If it is not, you put it in. Otherwise, so so we can keep track of this. Okay, so we will assume that D is more than C over epsilon square. Okay, so now what does ideal hash functions maps to? So ideal hash functions maps to real interval 0, 1. Instead be mapped to integers in the big range 1 to n cube. Okay, so so let's just try to understand. So 0, 1, instead we map into this big range. So when we were mapping into 0, 1, right, what did we saw? The minimum, if there were D distinct number, then it was partitioning into 1 over D plus 1 choices or parts. And that is why we took the minimum and did everything. But now think of this as like, as I told before, think of this that this is like 1 over M, 2 over M, 3 over, sorry, N, not M. And so on and so forth. Now, since H is uniform in this range, okay, so basically we are scaling everything, right? So I could have, so for example, how could we, so we could have also taken a new function G. What does it does? So I could have also defined a function from N. I'm sorry for this noise. Okay, so how could have done? So look, what does H of I maps to? Suppose H of I maps to some X in n to the power k. So we could have taken, defined another function G from n to 0, 1 as follows. How we could have defined 0, 1? You take G of I is nothing but H of I divided by n, right? So now you have scaled down everything between 0 and 1. Okay, so this is what is happening, right? So in other words, everything is multiplied by n. So now if H were truly random, what do we expect minimum hash value to be around, right? So if you expect truly random, then what happens is like you have made like there are n parts. So you have divided this 1 to n in n equal parts. So first will be like n over d plus 1, 2n d plus 1, so on so forth, d plus 1 into n by d plus 1. right? So yeah, so this is how it would have been done. So now what do you expect your kth hash value to be? Well, we expect tth minimum hash value to be around what? T times n d plus 1, right? Because we have just divided them into equal parts. So basically everything has become a multiple of it. So this is why, if you notice, what are we returning in our algorithm? In our algorithm, we are returning Tn by V, right? So what is Tn by V? Okay. So Tn by V, where V is the tth hash values, and we expect the tth hash value to be Tn by d plus 1. So what did we return? Tn by V, which is Tn by d plus times t plus 1, right? So this is perfectly fine. So we should have just written -1 here, okay? But since we are only interested, so like, I mean, we could have done -1. But since we are anyway doing number of values are far too much compared to, like, when it is small, we are anyway doing exactly, this wouldn't matter -1 if we are looking for 1 plus -1 approximation. And that is why we didn't do this, okay? So, okay, so this is why. So we expect the minimum hash value V to be around Tn by d plus 1, and hence we are doing what we are doing in the algorithm. Okay, so what is the best way to understand? Like, think that we are mapping 1 to nq to 0, 1 as a multiple of 1 over n, 2 over n, 3 over n, so on and so forth. And how can we define that function? Simply define g of I is hi of I by n. I could have also put that, but that would have made it a little bit difficult. So now if this is how it is, then what is your minimum value? Is 1 over n. What is your tth minimum value? Is like t over n, but into something, right? So when we push back up, we just divided everything with Tn over d plus 1. So like whatever we, whatever we impress to, we just multiply by that to get the exact one. Any question? Okay, and that is why TNV should be around d plus 1. Okay, so I hope the algorithm's intuition is very clear. So what is algorithm doing? It's basically picking a random hash function and picking an item and keeping certain threshold number of minimum hash values and returning the one which is tth smallest hash value c, so forth. Okay. Okay, so let's ask ourselves why this algorithm, when will this algorithm be bad? Okay, so okay, let's see. Okay, let d be actual number of distinct values in a given string. Okay, and we are assuming that d is greater than c over epsilon square. Let d be the output of the algorithm, which is a random variable, right? Now, what we are going to show to you, that probability that d is not too small compared to its minimum is 1 over 6. Probability that d is not too far up, like not too far away, is also 1 over 6. So probability that d minus d is greater than epsilon d is 1/3, right? So what we are able to achieve? We are able to achieve epsilon approximation with constant probability. And once we are able to do that, we can do median trick to reduce error probability to delta with order log 1 by delta parallel repetition. Okay, so now this median trick I will just tell you, but it's exactly the same. But now let's see what is happening actually. Okay. So this is, what do we expect D to be? Right? What do we expect D to be? Well, we expected D to be Tn by D plus 1. Okay. This is what we expect. Right? Why will we go wrong? Well, we go wrong because we needed to get values somewhere here, right? So why are we going wrong? So what are we returning? We return generally D plus 1, right? So this is going to be Tn by something smaller, right? So no, something bigger, because no, this is something smaller. So 1 plus epsilon times say D plus 1. Okay, so for purposes of cleanliness, let's just forget. For understanding, let's just forget plus 1. Okay, it will not affect us anyway. Okay, right? This is something smaller quantity, and this is like Tn, say 1 plus epsilon D. Now let's ask ourselves, look, what am I going to do? So your function h, right, looks at 1 to n, right, or looks at its stream, okay, looks at its stream a1, a2, dot, 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 am, m, and it maps somewhere here, right? It maps somewhere here, okay? Now, each ai is equally likely to go to one of these integers, nq, and then you have done everything. Now, why will I go wrong? Well, the only reason you could go wrong is that suppose kth value, kth minimum, tth minimum is mapped somewhere here, right? Or tth minimum is why? Because what are you returning? If tth minimum is between this range, then what will you will be returning? Suppose this is the range. This is the range. So if your tth minimum will lies here, then what happens? Well, whatever may be the value, you reverse it, right? So you are not going to give me anything more than 1 over epsilon by d, or nothing between, or this is wrong. This should be this is smaller number, right? So this should be 1 minus epsilon. This is 1 plus epsilon. Is this correct? Okay. Okay. So yeah. So if your tth minimum was here, then what will happen? 1 plus epsilon d, you will return either 1 plus epsilon d, some number d tilde, which is between, let's see, right? You will return some d tilde, or let's say we anyway call them d. So what will be your d value? D will be between 1 minus epsilon times real d and 1 plus epsilon times real d, right? So the only reason is that you will do bad because either tth minimum lies in this part of the green region, or tth minimum lies in this part of the green region. Or in other words, either, so what is the probability if I ask myself that d takes value less than 1 minus epsilon d? So if I ask what is the probability that d is less than 1 minus epsilon times d? have I done something wrong here? Shouldn't it be 1 plus epsilon? Yeah, it should be 1 plus epsilon, right? Because this is a smaller number and this should be minus. Okay. Sorry. I mean, I always confuse with this, but that is okay. So what is a chance that D is like less than or, okay, so let's ask ourselves, what is the probability that D is less than 1 minus epsilon over D? Well, it means this range, right? This range has how many numbers? Teeth minimum is not here. Like number of distinct hash values which lies in this range, right? This implies number of hash values that lies in pink region. I will, okay, is strictly less than K, right? Okay. Now you ask another question. You ask, well, what is a chance right? Okay. What is the chance that D is greater than 1 plus epsilon times D? So it means here, it means, let's say if brown color, it means in this region, right? Why? Like it means in this region, you have more than K values, right? Because that is why you will get something. So in this case, this implies more than K values, K hash values in the range. Okay. So this is the picture which we have to keep in mind. Okay. So what we wanted to estimate Tn over D, and we say, oh, well, what is the reason why I could be wrong? Well, the reason you could be wrong because your kth minimum could be part of the green region. And which part of the green region kth minimum is, it will tell us a different kind of estimates on D. Okay. So this is what we will try to, okay, so this is why I explained to you why. So this is our game plan. Okay. So let B1 to BD be distinct values in the stream. Okay. And Tn by V, where V is the tth smallest hash value stream. And each BI has to uniformly random bucket from 1 to n. Now you consider a bucket in interval 1 to Tn by D. Okay. Now the question is, expected number of distinct items hashed to this interval is like T. Okay. Because everything is multiple of, like it should have been D plus 1, but as I told you, right, just for clarity, let's just, okay. But D is less than 1 minus epsilon D implies that less than T hashed in this interval, right? This is what I was explaining before, that it means that in this interval, number of distinct values is T over 1 minus epsilon, whether what is expected is like T into 1 minus epsilon. So you expected many more values to be seen there, but actually you saw something much smaller, right? Similarly, if D is more than 1 plus epsilon D implies that more than T hashed in the interval 1 to Tn epsilon plus D, although you expected much smaller value to be seen there. Okay. Okay. So now we will use Chebyshov to analyze this bad event probability by a pairwise independence of hash function. Okay. So let's go back to picture, what we just draw, right? So, right? So this is what this is the picture we had, right? So implies if D is less than 1 minus epsilon by D, right? Right? It means less than K values, or not, I shouldn't say K values, T values, T has values when there, and that is exactly what right? Less than t value went in that interval, okay? Right? And if it here, it means that in this region, more than t has values went into the interval, okay? So this is our game plan, right? More than t has value in the interval when the t has, right? Now we will analyze this in a minute, okay? Okay. So, but something which I did not tell you or we didn't bother. Well, notice one thing. We chose h random from h, right? H is a function. So it is true that every guy item which is same, they will be mapped to the same person. But well, two different items could also be mapped to the same guy. In other words, there could be a collision, right? So you also have to take care that, because that will mess up your distinct elements, right? Which was not an issue when we were talking about idealized hash function, because probability of collision was 0. Okay, like we have such an uncountably many objects, the two objects will collide, is too low. But now things could collide, right? Because look, we can prove that there exists a hash function that it doesn't collide, but it could collide because we are just picking a function h which is random. But what we can show, which I will not show to you, and I will assume this is a simple exercise. Okay, is that since n is nq, the probability that there are no collision in h is at least 1 minus 1 by n. Okay, so we will assume for a moment that we have no collision. Otherwise, you also have to take into account the probability of this. But it is like a birthday paradox. So if you know, right? So in fact, anything over n square would have been good to get a probability which is very close to 1. Okay. And recall from the last lecture what I told you, that if you have x1 to xk, some random variable, where x1 to xk are pairwise independent, then the variance of x is nothing but summation of variance of x, we prove. So we will use this lemma. And we will also use some estimate on 1 by 1 minus epsilon, 1 by 1 plus epsilon. You can look into this lecture in the slides, but there are some, well, like just follows from the Taylor series of 1 by 1 minus epsilon or 1 by 1 plus epsilon. Okay. So let's do analysis of 1, and the analysis that other side will follow is more or less same. Okay. So what is the probability that d is 1 minus epsilon d less than 1 by s6? So let b1 to bd be distinct values in the stream. Recall that d is tn by v, where v is the tth smallest hash value. And what did we saw? That d is less than 1 minus epsilon d if and only if v is more than tn by 1 minus epsilon d, which implies that less than t hash values fail in the interval this. Now we have to analyze what is the probability that t less than t hash values fail in the interval 1 to this. So what we do, let xi be an indicator random variable, okay, indicator random variable for the element bi. And so that what is the indicator random variable? Well, it takes 1 if the hash value is less than whatever we wanted and 0 otherwise. Okay, so if xi is bad, it means it lies in this particular interval, then it is 1, 0 otherwise. Then what is x? Is a number that has to I. So probability that d is less than 1 minus epsilon by d is same as probability x is less than t. It means in this range, less than t hash values has been mapped. Now, okay, Okay. So since HBI is uniformly distributed in 1 to n, okay, what is an expectation of xi? Is probability xi equal to 1, and that is like t over 1 minus epsilon times d, because they are multiple of this, so and you divide by n, right? And this is, look, I'm ignoring some rounding issues for clarity of calculation, but so now by applying that 1 by 1 minus epsilon is at least 1 plus epsilon, so you can get that expectation of xi is 1 plus epsilon t over d. Okay, like what is more important is how the analysis is done, not what the real numbers are. Okay, now what is an expectation of x then? Well, expectation is summation of xi, so it is at least 1 plus epsilon t. Now recall that probability d is less than 1 minus epsilon d is probability x less than t. Now thus d is less than 1 minus epsilon d only if x minus its expectation is less than epsilon t. Now we will use Chebyshov to upper bound this probability, right? So for that, we need to compute the variance of this xi. So what is the variance of xi? So what is the variance of xi? So if you notice, variance of xi is a random variable, right? So it is expectation of xi squared minus expectation of xi whole square. But what is an expectation of xi squared? Right? So expectation xi squared takes 1 or 0, right? And expectation of xi squared is same as probability xi equal to 1, which is same as expectation of x. Right? So variance of x is nothing but something expectation of x and expectation of x whole square, which is less than or equal to expectation of x. Okay. Okay, this is what. And now we can use the upper bound on what is that called? Expectation. See, look, where here we used a lower bound, right? But we also had an upper bound to use, right? This was an upper bound to use for 1 by 1 minus. So this is what actually we have used here to bound. Okay. Now, once we know variance of each, we can just sum the variance. Right? What is variance of x? Summation I variance of xi, 1 plus 3 epsilon by 2 divided by t. Okay. So probability x is less than t is less than or equal to probability that expectation is like more than epsilon by t, which is variance of x epsilon square t square. So 1 plus 3 epsilon by 2 divided by c. Okay. Now, if we can choose C sufficiently large to ensure the ratio is at most 1 over 6. So this is where we are going to use that we chose C. So if you chose C is like 24, it turns out to be 1 over 6. Okay. And you can do a similar analysis for what is the probability D is greater than 1 plus epsilon T is very similar analysis. Well, T has values must fall in the interval. You set up the indicator random variable that it is this, you set up X. Now Y should be greater than T. Well, then you again compute expectation of Xi, use other bounds, use pairwise independent to sum the variance, and then finally apply Chebyshov, because look, this is the great point about Chebyshov. It's like it tells us the probability here and probability here. So whether x is less than t or x greater than or equal to t, it is upper bounded by this quantity. Okay, and again you can choose C sufficiently large that it is 1 over 6. Right. So this is what we managed to show. Okay, so once we are able to show this, what do we get? Okay, so now you can ask, where did we use the fact that D is more than C over epsilon square? Well, we needed to be more careful in analysis by 1 minus epsilon D and n 1 plus epsilon D. And since we need to round them to nearest integer, technically we have to use floor and ceiling. So if d is greater than c epsilon square, then rounding error of 1 does not matter and adds only epsilon d error. So for the clarity, we avoided this. But if you write a paper or something, you might have to use this. So what is our take-home message from here? So the take-home message is 3 things. Okay, so first is that what do you call median is a better is much well behaved with respect to outliers, because for that to go wrong, many random variables have to go wrong. That's one thing to take from here. So this was introduced. And secondly, so if you can first try to make some algorithm which is like for very idealized hash function, and then try to discretize it by taking a larger domain. So look, this is very different to compare to the way data structure people apply these things. In data structure, the range is generally smaller compared to the big universe here, but here we have made much bigger so that things are spread around and we can bound the variance from there. Okay. So and for the analysis, so look, when we assumed completely random, then we had this integration and then we took product of each probability. And now this is the place where we use the fact that we have 2-wise independent. So to use 2-wise independent, we needed to upper bound the bad probability in a different way. And how did we do? We said, well, this is where this picture was useful for us, that look, if we are estimating Tn over D, then this, well, why it is bad? Because so many objects went there, or so many objects went there. Then we set up our random variable, we computed its variance, and now for variance, it is just good enough that we have 2-wise independence, which we used, and that gave us the desired result. Okay. Okay, any question before we move to the next algorithm? Or any problem in understanding the algorithm? Okay. Okay. So this algorithm came earlier than the, so what was the space complexity? The space complexity eventually would have become order 1 over epsilon square log n time log 1 over delta, right? This is what would have been, okay? And we will see that it is like till 2002, this was the best known, but currently we have much better dependence. But you cannot get rid of the dependence of 1 over epsilon square, okay? Hopefully we will see a proof. So now I'm going to tell you an algorithm which is like called AMS algorithm, Alon, Matthias, and Szegedy. And this is from 1998 paper, which started the field. Okay, and it is slightly different way. So notice that the reason why I presented the first algorithm, because it was like, okay, it was trying to adapt the idea of this idealized hash function to a hash function by discretizing, right? So in some sense, it was trying to adapt this algorithm in this setting, okay? This is yet another approach to do this. And here is, before we go, let me tell you, okay. So suppose I have a hash function into n, okay? And suppose it is uniform over its range. Okay. If I ask you, and everything in expectation, how many numbers will H map with 0 at as the last bit? Any answer? Okay, my son has come, so I will have to move him out. So just till then you can think. Hello. So how many numbers will H map with 0 as the last word? Of course, in expectation. Anybody?
Half.
Yes. Roughly half. Okay. So now we ask how many numbers will H map with 0, 0 as the last bit? Anybody?
One quarter. 1/4.
Yes, correct. 1/4. So we can similarly say that if the number, how many numbers will H map with say 0 power L as like roughly n over 2 to the power L, right? Okay. So this is like a pyramid, right? So, okay, this is like a pyramid. Half the elements like this, half the elements like this, and how many it will see with 0 power log n is, suppose n is multiple of 2. We will always assume is multiple of some. Okay, so let's start. So this is what we all agreed, that it like there will be like n by 2 elements, we will see roughly n over 4 elements, we will see roughly n over 8 elements, and so on and so forth, right? So if we are at the nth level, right, that is like 0 power L, then we should see n to the power 2L, and at the core we'll just see one element. Agreed? Now suppose we have d distinct elements, okay, which are coming in stream. Okay, d distinct elements are coming in the stream. Now let's ask ourselves, out of these d elements, how many will you see at the 0th level? Anybody?
Half.
Exactly. I mean, so you will see roughly d over 2. At the next level, how many will we see? Exactly. So like this subsample of d elements also will behave exactly the way the normal elements behaved. Okay. So what does that tells us? It tells us something interesting then. Okay, at some point, at some level, we will stop seeing elements, right? Right? Roughly at which level will we stop seeing these elements? Anybody? Which level will we stop seeing, or we will see exactly one element?
Log D.
Exactly. So log D. And beyond that, chances that we will see any element at all is 0, right? So basically, if we knew which highest level our value is, we are very good, because then what should be the algorithm? What should be the algorithm returning then? 2 power the level, right? Do you agree? 2 power level is a good estimate for distinct elements. Is the intuition clear? Anybody? Piotr, is it fine?
Yes, it's fine for me.
Yeah, so this is what the algorithm will be do, okay? And it's very easy to see what is the highest level, because what were we doing? We were just checking 0 to the power L. Well, I look at my hash values, I look at how many bits, how many numbers of zeros it has at the end, and I just map it to that level, okay? So this is what this necessitates this definition. So for every integer p greater than 0, we use zeros p to denote the number of trailing zeros of p in binary. That is, it denotes the number of zeros that the binary representation of p and sin. Or in math, it's a maximum I that 2 power I divides p. Okay? And what is my algorithm? My algorithm is basically a 2-wise independent hash family from n to n. We choose h random from h. We initialize z is 0. Okay? And I just want to remember which is the highest level of this pyramid any of my h maps to. Right? So AI is a current item. I look at zeros of h of AI. And when I say zeros of h of AI, you write in binary, right? You see number of zeros, okay? And now Z is storing the highest level of some number it has seen so far. If the current number of zeros is larger, then we update it, and that's it. And what are we outputting? 2 power Z. Right? So this is an end of the algorithm, right? So why it works, not works, we will see in a minute. We'll make it formal, but it should tell you from this intuition that this is what it is trying to see, right? That we do not expect to see too many elements at a level, like at highest level, we expect to see just one element or few elements, okay? But lower level, we will see more and more elements. So if we knew the highest level this is, then 2 power that level should be a good estimate for the number of distinct elements. And this was an idea of Alon, Matthias, and Szegedi. Okay? So any question with respect to the algorithm itself? Okay? So look, there are 2 parts. One is, do we understand algorithm? And second, do we understand its analysis? So firstly, let's try to, so for simplicity, we'll assume n is the power of t. So memory is like one value. So like we are just remembering z, right? So order log n bits. Also order log n bits to store hash function, and processing per time, all you are doing is comparing hash values and one comparison. So it's like this is also some order log n, right? So this is very clear that this algorithm takes just order log n bits to store number of distinct elements. Okay. Okay. So I have already explained to intuition that after applying the hash function, HOI is uniform in 1 to n, right? So probability that it has more than t trailing 0 is at most 2 power minus t. See, it has more than t trailing 0 is at most 2 power minus t. Therefore, at least in expectation, if we have d distinct numbers, one of them may have log base 2d trailing 0. So, and we now just turn this intuition into the rigorous proof. So suppose B1 to BD are the d distinct elements. Okay. Fix R. So we are fixing R, and let XRJ be an indicator random variable so that XRJ equal to 1. Oh no. Okay. Please ignore these things. Okay. Okay. This, please ignore. There's some typo here. So XRJ is an indicator random variable so that XRJ is equal to 1 if number of zeros is at least R, and what is YR is J in D XRJ. So those elements, distinct elements who has at least R zeros. Okay. So YR is the number of distinct element whose hash values have at least R0. Okay. So now let's try to analyze R. So HBJ is uniformly distributed in N. So what is an expectation of XRJ? So what is this probability that zeros of HBJ is at least greater than equal to R? Well, so look, so let's assume that, as I told you, that let's N is like 2 power R. So how many integers in 1 to N will be there whose has at least R0? So we at least need last R numbers to be zeros, and I don't care what is here. I don't care. So how many such numbers will be there? 2 to the power L minus R, right? And how many total numbers are there? N, which is 2 power L, which is equal to 1 over 2 power R. So this is basically holds with equality. Okay. So it implies that what is an expectation of YR is like expectation of summation XRJ, and there are D values. So D to the power 2R. Okay. Now, these variables XRJ and XRJ prime are pairwise independent because H is 2-wise independent. Okay. So, which implies that for variance of YR is nothing but summation variance of XRJ. Now, what is the variance of XRJ? The variance of XRJ will be E expectation XRJ whole square minus expectation XRJ whole square. And as I told you, for indicator random variable, expectation of square is expectation itself. So, and this is another positive quantity, so we can less than equal to expectation of RJ whole square. Okay. And as this is same as expectation of XRJ, so variance is same as the expectation, like or variance is upper bounded by its expectation. Okay. So now, so what is YR? Is the number of distinct elements whose hash values have at least R zeros, and what is expectation of YR is D over 2 power R, and what is variance is like D over 2 to the power R. Okay. So now let's apply Markov. What is the probability that UR is greater than 0? Well, it is same as probability. So what is meaning that probability that UR is greater than 0, right? Meaning, what is the probability that like there is at least one element with R zeros, right? So probability that YR is greater than 0 is probability YR at least 1. And then if you apply Markov, what is it? This is less than or equal to expectations, because what is probability x greater than or equal to a is less than or equal to expectation of x divided by a, which is expectation of yr, which is d over 2 power r. Okay. Now, what is the probability that yr is equal to 0? Right? It means, when will yr be equal to 0? Right? No value. It means yr minus its expectation is like too far away. Like yr, like there's some expectation, right? So it is why it is 0 is because nobody has gone here. So everybody has like its expectation is, it is not close to its expectation, right? So what is its expectation? So, and we are looking for 0. So expectation is also d over 2 power r. So I'm telling you, what is this? What is the probability that yr is equal to 0? So it varies from its expectation by the same quantity as its expectation, which is same as variance yr square d by 2r whole square. And what was variance of yr square? Was upper bounded by, variance of y square was bounded by d2 power r divided by d2 power r square, so which is d square or d over 2 power r whole square, which is this and this will get cancelled, and we have another d2 power r which will become 2 power r divided by d. So let z prime be the value of z at the end of the stream, and d prime equal to 2z prime be the estimate of d. Let's ask ourselves, I want to say that d prime is not too far away from d with constant probability. Okay, so in other words, so analysis for some c greater than or equal to, so is it too large? So let a be the smallest integer so that 2 power a is greater than cd. So what is the probability that d prime is greater than cd? Right? What is the probability that d prime is greater than cd? It means there is ya. What does ya tells us? Ya is number of zeros, like ya is basically, if you recall, what is ya? Number of distinct elements whose hash values have at least are 0. So probability that d prime is greater than cd, it means at least one hash value has more than a0. It means ya is greater than 0. But what is the probability that ya is greater than 0? Well, we just have applied Markov, and it is upper bounded by d over 2 power r. So it is d over 2 power a. And now what did we assume? 2 power a is greater than cd. So if you do computation, you will get 1 over c. Now ask ourselves, is it too small? Well, let b be the largest integer so that 2 power b is less than d over c. So d prime is less than d over c, right? It means for the bth value, there is no integer which has, it is the largest integer that 2 power b is less than d over c. It means yb, the largest integer for which this happens, at that there is no hash value which has mapped. So probability is that yb should be equal to 0. But that is just exactly we computed here, right? Probability that yb is 0 is upper bounded by 2 power r divided by d. Right? So it is 2 power b over d. And with our choice, this is less than 1 over c. So what did we show? Now if you take union bound, this algorithm gives you that 1 by c, 2 by c approximation to the number of distinct elements. Okay, so this gives us an approximation to 1 by c, 2 by c approximation. So what do you mean by 1 by c? So the number is between, so our estimate d prime is between d over c and c times d with probability at least 1 minus 2 over c, because this is the error probability which you bounded. Okay. And if you can fix any constant, so for example, if you fix c equal to 3, then you get that factor 3 approximation with probability 0.333. Okay. Now, but suppose we wanted to get 1/3 delta approximation. So that probability that d prime is within this range and it is at least 1 over delta, 1 minus delta. Well, use the median trick again, right? So you run several things. Okay. So if you want to boost the success probability, all you need to do is run your independent estimator several times, find the answers, and give the median. So if your independent estimator had a constant probability, you can get that constant probability, but so error will not improve, but your success probability will increase by median tricks. So what you can do, so by running log 1 over delta parallel and independent copy of the algorithm and returning the median, and this time and space will be ordered log 1 over delta log n. Okay. So, but however, we wanted an epsilon delta approximation to the number of distinct elements, F0. I have already given you one algorithm, but I will give you another algorithm, okay, which is kind of very useful strategy or technique which is applied in streaming algorithm, which is called geometric sampling. So I wanted to introduce that via this example. Okay. So, but before that, is there any question or any algorithm, on this algorithm? Okay. Right. So if you notice, it's like it is all about understanding what should be our estimate B and what should be our estimate B, right? And then it is all about making sure that if you're using, sometimes we will use not two-wise independent hash function, but larger wise hash function, and use that to conclude whatever we wish to conclude. Okay. But we use two-wise independence just to apply that set up some indicator random variable x1 to xn, and which is sum, and to say variance of xi, right? This helps us in some sense upper bound the variance in terms of expectation. So that is the main deal about it. Okay. Now, how do we go about making this proof epsilon delta? Okay. So all we were able to achieve, notice from this algorithm, is that we can get a constant factor approximation. Okay. We can get a constant factor approximation. Okay. So this is a factor 3 approximation, or we can actually get it for any factor c greater than 2. Why c greater than 2? Because if you notice here, like we had 1 by c, right? So 2 by c comes here. So c has to be more than 2 to make any sense. Okay. This is why c has to be greater than or equal to 2. Okay. No other reason. Okay. Okay. So for any this, we can get this. But this is a constant factor approximation. We are not saying that d prime is, well, it is 1 minus epsilon d prime, 1 plus epsilon d prime is this. We would like to say this is 1 minus delta. But at least, so ABS did not do this. Okay. So now I will tell you an idea of distinct elements via geometric sampling, which will use the AMS algorithm as a black box. Okay. Okay. So what is the geometric sampling? So let me give you an overview or idea. So it is a stream of samples having elements from 1 to n. Okay. So the main idea is that we pick a hash function from 1 to n to 0 to log n from a two-wise independent family with elements having geometrically decreasing probability. So what is the probability that hi takes a value j is 1 to the power 2j plus 1. So for example, it takes, so for example, it takes 0 with probability half, okay? It takes 1 with probability 1/4. It takes 2 with probability 1/8, right? So on and so forth. And for j equal to log n, it is basically 1/n, okay? So now notice this hash function is not uniform in its range, okay? So this is what is like, so this is like a geometric sampling is basically like a sorting in some sense of streaming, okay? So this is what is, so this is what, so we would like to pick a hash function with this property, but how do you get such a hash function? Okay, well, that is not very hard. So how do we implement such h? You select some h prime from 1 to n from a 2-wise independent hash family and define hi to be the index of the least significant bit of h prime I written in binary, right? So for example, this is same as zeros of h prime I, right? For example, what is an h prime I of 1 1 0 0 0 0? So remember, this is called 0th bit. This is called first bit. This is called second bit. This is called third bit. Then what is hi of 3? Hi is equal to 3, which is same as zeros of h prime I, like number of trading zeros, right? So least significant bit. So so now if you're starting from numbers 1 to n, right, h prime is going to give you a binary number between with log n bits. So now based on what is its bit, you will do 0 to log n. So now if h prime is uniform from 1 to n, how many numbers will you see with the 0th bit? Of course, half, n by 2. Secondly, with first bit, 1/4, so on and so forth. So so you do not pick this h, but you first pick h prime and you define h by looking at where it maps, okay, and then taking the least significant bit, okay. Is the idea clear of how to select such h? Okay. Okay. Now the question is when to use. Well, if we know how to solve some special cases and want to combine these special cases for general case, then we try to apply geometric sampling. Okay. So notice what happens. H partition the stream into log n plus 1 different substreams automatically, S0 to S log n. How? SR is the stream restricted to all those. So think of this way, A1 is coming, A2 is coming, AM is coming, right? Now, you pick out some. What do you pick out? You pick out those guys from here whose least significant bit is R, right? So for each of them, there is some least significant bit, 0 to something, right? Log n, right? So it will partition into 0 to log n different substreams. Like they're not continuous, right? And what we would like to do is that each SR, like each substream, is then fed into some separate data structure DR. Okay, so basically we say, oh, for such items, we will process in a different data structure. For these items, we'll process into a different data structure, so on and so forth. And at the query time, like it's a problem specific, like do we take solutions from different data structures, combine them and give you a solution, or we look at a solution at what is that called? From one data structures and give you a solution, and so on and so forth. Okay, so now in this language, let's go back and look at AMS algorithm. What is happening actually? Okay, so basically, think of this that we have a data structure. D0, D1, D2, D log n, right? So H comes, I look at zeros of H of AI, and what do? Well, I So I feed into the ith di when I say, well, is it non-empty or not? If it is non-empty, then just add this element. So this is all that you are to choose. So, and what is the query? Largest I such that di is non-empty, right? So in some sense, we are also implementing this here, but our data structure is like in some sense simple, trivial, and it all cares about whether there is some element or not with I bits or not, right? And query is which is the highest high. So whichever is the highest high, you take that index and you output 2 power z. Okay. Now we will make this nature of algorithm of AMS into slightly non-trivial. Okay. Any question? Okay. So this is what I meant by SR is then fed into some separate data structure, and you take solutions from different substreams, so different data structures, and you get answer for the whole stream. So that's the whole idea. Okay. So in geometric sampling for distinct elements, here's our special case. Okay. We are promised that D equal to F0 is at most K and want to compute F0 exactly. Can we do this? You're promised that the stream has at most K distinct integers or distinct numbers. Can we compute this exactly? Well, yes. I mean, you can just keep any data structure like priority queue or something. So basically, you have a data structure, you keep at any point of time K elements, okay? And you check whether new element comes, whether it is same or not. And if it is not the same and the number of elements which are inside is less than K, you add that to data structure, right? That's it. And if it's K plus 1 comes, you can just set a bit, okay, more than K, okay? So this can be implemented into K log n bits because each number could have log n bits, okay? And we will call this TS or trivial data structure, trivial structure, okay? Okay. Now we pick K some C over epsilon square as again we do not want to okay. So we will have several okay, so let me give you first, let me give you rather than giving you algorithm first and then intuition, let me first give you an intuition. Okay. So what is happening now? Okay, so we'll fix K equal to some threshold C over epsilon square. Okay, we'll fix this. Now we will have a different data structure, D prime, D0, D1, D log n. Rather, let's not draw like this, like a box. D0, D1, dot, 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 D log n. Okay. And here's a D prime. I'll tell you what is the utility of D prime. Okay. So now an item AI comes, okay, I will feed him first to D prime. Just in case if there are a number of distinct elements is upper bounded by K, then I will use this D prime to tell me where it is. Now what I do is that now what does this algorithm does? Given AI, it computes the least significant bit of, and of course we have a hash function, h of AI, and suppose this is B, or then it will map it to some dB. So same element will be fed to D prime as well as to corresponding data structure. Okay, so this is what will this do. And what does query do? Okay, what do we do for query? So for query, we'll do as follows. Okay, so query, first we'll check D prime, right? If D prime is less than K, right? Then we will just output exactly whatever we wished, okay? Otherwise, suppose we have more than C over epsilon square elements, right? Now, what I will do is that let's go back to AMS algorithm. What did we do to the AMS algorithm? We looked at the highest index which was non-zero, right? And that was good enough for our purpose. But notice, in expectation, D log n has one element, but really it will have one element, right? It could have, like, chances that it will have some 5 elements is much, like probability that it will have 5 elements is much higher than just one element. So in some sense, like, what is important for us are layers close to where the highest layer, which is close to D log n, that is important for us, okay? Now, we will choose a number, and I will explain to you why we choose the way we choose, which is like not the highest, but we'll say, hey, so look at the highest. How many elements do you see? Some constant number of elements, right? With very high probability, the highest guy will see constant number of elements, and we will make sure that that constant is not more than K. So every data structure is like a trivial data structure. So I'm just trying to store, oh, does D0 contain K elements or not? D1 contains K elements or not? So like in every stream, each data structure will try to save K distinct elements. And our belief is that the highest data structure, we have chosen K in such a way that all the elements with that many number of like least significant bit being that R star, like all the elements we are able to store, because the K, the threshold, is large enough that whatever the variance could be, we are able to tolerate that, okay? And then what will the algorithm will be 2 power that into the number of elements there, and that will be our output. So is the overall idea of the algorithm clear? Right? So what are we trying to achieve? We are trying to achieve is that, look, I want to go to the top, but top, I know that it cannot contain more than some constant number of elements. Great. Let that constant be governed by this K. And what is my belief, or what is my, so whenever I say belief or expectation or probability, is that all the elements with that many number of bits will be stored explicitly there, right? And we will use that quantity to give the estimate to the number of distinct elements, okay? So this is the whole idea, okay? So, look, and I'm on purpose, I have not used the H0 to log in because, but you know, this is what is happening by, so what did I do? So whenever AI is a current item, I feed AI to TS prime. Okay. This is not correct. It should be D prime, okay? And I think, okay, so, okay, no, this is right. So we have established for each, so with the trivial structure, and I should have used better notation. This is just not right. This should have been d prime, d least significant bit being h of ai, or d0. So it basically tells us, given ai, please feed it to d prime and please feed it to this. And what I'm doing, if query of d is less than k, then output query d prime, like output, like you exactly. So with probability 1, you are succeeding. Okay. Else, I'm going to output 2 to the power r star plus 1 query dr star out, where d power 2 r star plus 1 is like order 1 over epsilon square. Okay. Now this sounds, why did we choose r star the way we chose? That's the first question. And here, what am I doing? So why we choose r star the way we chose? Okay. Secondly, from where do we get d? Right? Right? You get my point. I mean, I'm saying I want to compute distinct elements d, and I'm using d in my algorithm. Right? So there are two things which I must tell you. Okay? So we will see that. So going back to analysis of AM, okay? Okay. So we had B1 to be the D distinct elements, and for fix R, now WRJ be an indicator random variable, so that WRJ equal to 1 if number of zeros is exactly R. So WR is again summation YRJ. So ZR is the number of distinct elements whose hash value have exactly R zeros. So what do you mean by that hash value has exactly R zeros? It means you have R zeros and 1 and then anything else. So basically you are fixing R plus 1 last bits. So this is why you will get 1 over 2 power R plus 1. Okay, same computation. And same with expectation Z, now with extra plus 1. Okay. And again, because we chose hash functions from this, you can show that variance of Z prime is upper bounded by D to power R plus 1. So expectation and variance are same even in this case. Now let's try to see what happens. So what is Z R star is the number of distinct elements whose hash value have exactly R star 0. Expectation is this, variance is this. Okay, let's call variance of G tilde this as D tilde. Okay, so I'm going to call this number as D tilde just for the simplicity. So what does Chebyshев inequality tells us? That probability that Z R star minus D hat is greater than alpha D hat is 1 over alpha square. Why? Because what is this? What the Chebyshef inequality says? This is nothing but variance of Z R star divided by whatever is here whole square. So it would have been alpha square D hat. Okay, but what is the variance of Z R star? Is D by 2R is same as D hat, right? So D hat by alpha square D hat. So you get this. So what does this imply? It implies that probability that the Z R star is between D hat minus alpha root D, D plus alpha root D is 1 minus 1 over alpha square. But what did we choose our D to be, right? So this is exactly the reason why we were choosing, like, okay, so what is its variance? How much can it vary from its variance? Like, or from standard deviation, how much can it vary from standard deviation? So if it is 1 over epsilon square, then it can only vary from 1 minus epsilon. So this is what is happening here. So from here to here, how do we get? Well, of course, I'm like missing, like simplifying several things. But if you look at this, D hat minus alpha root D hat is nothing but, I can take D hat common, then I get 1 minus alpha times D hat. Is this correct? No, 1 over D hat, right? Because D hat goes inside, D hat whole square, D hat get cancels, so D hat, okay? But now What did we know d hat is? Like say d hat is, this is what we chose d hat to be, right? 1 over epsilon square. So this becomes d hat 1 minus alpha times epsilon, okay? And similarly here, right? So what are we able to show? That if we chose r star the way we chose, then the probability that now that the estimate at z star is 1 minus epsilon and 1 plus epsilon approximation with good probability, right? So like what choice of alpha, this is completely dependent on that big C which we are choosing in the beginning, okay? So we can make the maths work. So this is an idea why, right? So this is what we get, and that implies that choosing C large enough, we can also guarantee that 1 plus epsilon d hat is less than k, so that we output z star correctly with high probability. You get my point? So I can choose C large enough that at the top level we know that is constant, right? So you choose k C such a way that whatever is the expected value at the top level, 1 plus epsilon d hat, is less than equal to k, and so z star with very high probability will contain all the distinct elements with r star number of zeros, right? And that is what exactly is happening. Okay, so, and that is why when you multiply query dl star by 2r's plus 1, it gives us 1 plus epsilon d with large probability. Okay, so this is an overall idea of how geometric sampling works. So you always choose the range where the variance is like closer to what you wanted, okay? So that you can prove this inequality. And so what R star will we choose? So R star should be just a function of epsilon square or something. We'll come to that later. So this is an overall idea of how the geometric sampling works. So now let's go back to our geometric sampling algorithm. Now at least I understand why are we doing this, okay? Because this is what allows us to get 1 plus epsilon minus epsilon algorithm. But how do we get D? I mean, that's an important question. Who gives us D? Well, in fact, any good approximation of D will work, right? Because all we needed is some constant times 1 over epsilon square, right? So to get D prime, we'll run AMS algorithm in parallel, right? And what I mean by this, so here is a geometric sampling algorithm where, so now you notice we also have Z as 0, right? Z stores max Z0 H of AI, and we are running that another algorithm. Now rather than comparing it with D, we are comparing with 2 power Z. And what do we know 2 power Z? Well, you could get any good factor approximation algorithm. So for this algorithm to succeed, you need to succeed. AMS algorithm need to succeed, and the second algorithm need to succeed. So, but this is why I made our AMS algorithm with constant C. Well, you can get 25 approximation with, and you can succeed with much, much higher probability, right? So now analysis. Now you need G and H, they need order log and bits. J needs log and bits. D prime or Di takes order k log n, order epsilon log n bits, right? Because each Di has to store some k numbers, which is like roughly C over epsilon square. So order epsilon square log n bits. So in total, because we are running something like log n plus 1 data structure, there's an extra log square n bits of memory to get what? Epsilon comma fixed constant approximation, right? So you can get, this only will give you a fixed constant approximation. It will not give you delta approximation. But to delta approximation, what do you do? Well, if this is what you wanted, you can apply median trick by running log 1 over delta parallel an independent copy of the algorithm and returning the median. So you will have extra log 1 delta running into this, okay? And what we saw, so we saw 3 algorithms for this. One was an algorithm which gave 1 over epsilon square log 1 delta log n. That was the first algorithm, and estimated these such that with probability 1 minus delta. But actually the best known algorithm takes log 1 by delta epsilon square plus log n bits, and for any fixed delta this meets the lower bound within constant factors. And both lower bounds and upper bounds proofs are quite technical, so if someone wants to read, can read. There's also another object which people study, something called continuous monitoring. So at any point of intermediate step, I would say, give me the estimate. Means give me the number of distinct items which you have seen so far. And that also can be done in log n plus log 1 over delta epsilon squared plus log n bits. But what about deletions? I mean, maybe some deletions are allowed, and that can also be done. But for that, we need a different strategy, and we will see in week to come or something. Okay, so I gave you 3 algorithms. First one was this algorithm. Second one was AMS algorithm, which was just a constant factor approximation. But it was a very nice idea with this. This is also called watermark algorithms. Like it's like a watermark in the river. What is the highest mark you can reach, and that. But then we use this basic idea of geometric sampling to turn AMS algorithm into like epsilon delta algorithm. But notice that there's an extra log square n bit, like extra log n bit here. So this is not the best than the first algorithm, but I taught you largely for the pedagogical region. Okay.